Well, welcome back. A week rolls by and here we are once again. Slightly different spot in the garden, and you can probably guess the reason why. If you're a regular viewer, listener, you perhaps can even hear a slight hint of it in the background. But today is National Children's Day, so my beloved neighbours are sharing their music with their friends, me and everybody else within a 5-kilometre radius, which you might argue is a very appropriate way to celebrate empathetically with children. Make a lot of loud noise and damn all those around you. But never mind, rant over. This week I found myself plunging down a mathematical rabbit hole. I do every now and then, from time to time, I receive prompts on YouTube to watch interesting mathematical content. Now, again, if you know my backstory, you'll know that whilst I did a degree in mathematics, I probably didn't spend nearly enough time studying. And I am at best an armchair mathematician, a sort of pseudo-mathematician. I know a little bit about it and I can follow a few arguments, but really I never reached a significant level at all. More than enough to teach high schools, and more than enough when I was teaching high schools to give them some idea of the depths and directions that things might take. And for someone like me, our modern age of high quality YouTube content is truly fantastic, because the videos about maths make even the most unintelligible, the most obscure, abstruse sort of topics actually accessible for, I wouldn't say anybody. The video I found myself watching this week really wouldn't have made a lot of sense to someone who didn't have some sort of maths background. But it was enough for me, and fascinating stuff. And strangely linked in with what I've been talking about. There's a video in question dealt with what is called in mathematics the Langlands program. Langlands superior, Langlands plural. I'm getting a bit jumbled up here. Blame it on the background mental stress. So the Langlands program, named after Robert Langlands, who was a top flight mathematician, occupied an important position at the Princeton Institute for Advanced Studies, and indeed occupied Albert Einstein's office from his time way back when. So what is the Langlands program? Well, it was a very ambitious idea to kind of penetrate the underlying mysteries of mathematics. In particular, what Langlands was sort of suggesting was that we look at mathematics as sort of independent subjects. And indeed, I say I don't really understand much of any of modern mathematics. I understand the gist and the sort of the summary for the layperson, but not the real technical details. But it's fair to say that over the last 100 years, mathematics has reached a point where nobody understands all of mathematics. It's just too wide a subject and covers such diverse material. But Langlands suggested that actually these separate continents of mathematics, and from the point of view of this video, I'll go with one of the multitude of metaphors used. I watched a couple of different videos about the program, and they use different ways of explaining it. But let's think of mathematics as a map. And if you looked at a map of the globe, the different areas of mathematics would be sort of equivalent of the different continents. So one of the continents is what is called number theory, which has a very ancient and special place in the story of mathematics. It's essentially the study of the properties of whole numbers, but it goes in much deeper than that. And another continent might be harmonic analysis. Harmonic analysis is a sort of deals with functions, and you might think of an example of something that sits inside the realm of harmonic analysis as trigonometric functions. Just one of a multitude of little creatures inhabiting the continent of harmonic analysis. And there's others, geometry, mathematical logic, and so forth and so on. But what Langlands seems to be suggesting is that rather like if we looked at the map of the world, the continents all seem like separate entities. In fact, they all simply parts of the whole. And in a way, I suppose, forcing this comparison, you can think about how the continents all once were actually one sort of joined together landmass. I believe Pangaea, sure, stand corrected. And you can kind of see that, how South America and Africa could fit together quite nicely. And then the wonderful process of continental drift happened, and sort of comparable to intellectual drift, and the different areas sort of drifted apart in mathematics, just like the different continents shifted and relocated where we find them now. But Langlands suggested that no, they're all actually deeply and profoundly connected. And the powerful idea here, and this is where it kind of links back, sort of circles around and joins in with what I've been talking about over the last few weeks. The powerful idea is that a result that you might prove in one area may be helpful in another. And in fact, in the videos, the classic modern example they use, and the greatest accomplishment so far that could really fit into the enormous umbrella that is the Langlands program, the most well known is the solving of Fermat's last theorem. I've spoken about this before. There's a phrase I've used time and time again, because like so many people, after a certain point, one does repeat oneself. But it's always with a slightly different flavour. So I think of it as preparing a curry, but the ingredients might differ somewhat. So Fermat's last theorem is this remarkable result, postulated, conjectured, but suggested as a theorem, as if he actually had a proof. Because Fermat, in fact, said, I have a wonderful proof, but the margins of this book cannot contain it. He was annotating Diophantus's book on number theory, on polynomial equations. And essentially what Fermat's last theorem says is that whilst we have Pythagoras' theorem for squares, a squared plus b squared equals c squared, there is no such similar theorem for higher powers. There's no a cubed plus b, or no solution rather, not theorem, solution. A cubed plus b cubed equals c cubed, where a, b and c are whole numbers. Just one would do, but there are none. There's an infinite number of solutions for Pythagoras' theorem, and a result that one could prove in high school maths. Now, this was incredibly difficult to solve, and for 350 years people blundered around in the dark, made some progress, but it was somewhat limited. Eventually got solved when people were able to find a bridge linking two very different areas of mathematics, the elliptical equations in, now I'm probably getting this the wrong way around, so I won't even pretend, elliptical equations and modular forms. And modular forms are a sort of subset, I think I've got this the right way, or a thing in number theory. And elliptical functions are something that reside in harmonic analysis. And eventually a very brilliant way of bringing these together came about, first through a conjecture by two Japanese mathematicians and a Frenchman, Frenchman. And if one could prove that conjecture, it suggested a sort of very clever way could be found, a bridge between these continents of mathematics, and you'd get, popping out the other side, a proof for Fermat's last theorem. In fact, it was a proof by contradiction using a third result in mathematics. And eventually Andrew Wiles, who was also at the Princeton University, British mathematician, he produced the final sort of coming together of these two different areas of mathematics, these three different results, and lo and behold, it was a proof of Fermat's last theorem. Now, I've taken a long time to say all of that, which is a pity, because I have so much else to share with you. But there we go. Let's just try and bring it neatly together. I mean, you can see that when I'm talking about a mathematical result, that this, in essence, is a result which is thinking by analogy on a very deep level. You are finding links between very different things and formalizing them, and a result that you get in one area, or that you can't get in one area, you can solve very neatly by finding a bridge to another area of thought. But this solution of Fermat's last theorem was just a small icing cherry on the cake of Langlands' program, which is much, much more vast. And so it struck me watching this video, and I'll finally get to the point. It struck me that what Langlands was trying to do was produce, as they said in the videos, a general unified theory of all of mathematics. And in a way, this is what self-actualization is all about, perhaps, on a very deep level. What we're trying to do is find a unification of all the disparate parts that make up our life, and sort of packaging them together in a coherent whole that is us, the unique individual, me, you. And most of the time we see the elements of our lives as these little individual minutiae details floating around in very separate areas. And what we need to do is look for a way of pulling it all together. And I suppose that way might be found in our values, in deep ideas and principles, and in glorious pursuits for something that lies well beyond our lifetime. So that's it. As always, a very esoteric, muddled sort of video. Make of it what you will. It's at least distracted me from the tedious music that my neighbours are sharing. I can't avoid it. I need to go back to the house and fill in some important bureaucratic documents. While doing that, I will probably blast something more to my liking as loud as I possibly can and try and drown them out. Anyway, trust your lives are filled with joy. Let me know what you think in the comments below. And until next week, from sunny Brazil, ciao.